In the last video, we finished the boring but important game state controls. Today we're building the final UI element, the on-screen display. I'll make a new file for that. For inputs, we'll need the score counters for each player, which we don't have yet, the horizontal and vertical UI buses, the ball counter, the player up signal, and attract. The only output from this module is the score line that feeds into the video mixer. This time we'll need to make some parts. We need 74151 8-to-1 muxes, the 74488 7-segment decoder, and a 555. Let's make that mux first. For I/O we have the 8 input lines, the 3 selector lines, the enable line, and the regular and inverted outputs. If the chip is enabled, we simply use the selector as an index into the input bit array value, and finally assign the inverted output. For the 7448, we'll need the binary coded value, the ripple blanking input, the blanking input / ripple blanking output, and lamp test. She then puts out the 7 segments. This won't be a 100% compatible part. BI/RBO is hard to model, so this port will be input only. We're not using the pin in this design anyway. We need an always block for the procedural logic. If the lamp test is on, then all segments are lit. If the blanking input is on, or if ripple blanking is requested and the input value is 0, we blank all outputs. Otherwise, we decode the input value into the proper segments. This is stupid. Let's just decode the hex value. It will be self-documenting. I'm sure you've done this before. Instead of the strange-ass characters after 9, we'll put out proper hex. Not that it's used here, but it's nice to have. We also need to make a 555 for the score flash timer. If we plug the RC values into our handy-dandy calculator, we can see that this one has a 250 millisecond period at a 50% duty cycle. For all required timers, we can see that the shortest interval is 10 milliseconds and the longest is 1.2 seconds. The ICE40 has an internal 10 kHz low frequency oscillator with reasonable accuracy that we can use for timing these. I think we'll still divide that down by 10 so we have a nice 1 millisecond pulse to work with. I'll start a new clocks file and add a 1 millisecond module. I could call it 1 kilohertz, but I think 1 millisecond is easier conceptually for what we're doing. We're only putting out the clock line. This code will let us drive a wire from the internal low frequency oscillator. We'll need a small reg to hold our divider count, then add an always block triggered on the 10 kilohertz line. To divide this by 10, we need to count through 5 positive edges, then flip the output and reset the counter. And that's it. Back to main and instantiate this near the top. We use that 1 millisecond line in a few places. To test, I'll pipe that output to a debug port. I need to use a non-blocking assignment here. Turn that on. Pretty close to 1 kilohertz. For the paddles, we were doing analog to pulse width conversion, so we needed real external parts. Here we're just using it as a timer, so it's going to be fake. We need other fake timing stuff too, like the 74123, so I'm going to start a separate file for these. I'll make a 555 with the 1 millisecond clock, an enable line, 2 parameters for the timing, and the output. You can do this differently, like use the period and duty cycle. I'm too lazy. We'll need a counter to hold the timing ticks and a state tracking variable. In our always block, if she's enabled, we start by bumping the timer, which is used to count both on and off time ticks. Then, if the output is on and we've reached our on limit, we turn off the output and reset the timer. If the output is off and we've reached our off limit, we turn on the output and reset the timer. If she's not enabled, we clear the state and the counter. And finally, we turn on Q if enabled and we are in the on portion of our timing cycle. Let's test one of those with 25 milliseconds for the on time and 75 milliseconds for the off, just to make them different. I'll route the output to a debug pin and throw that on the scope. Looks about right. We can also hook enable to button 1, set the normal 250 millisecond timing, and drive that to an LED. We'll just take over EGL. Works as expected. We'll start with the display funnel, but since there are a lot of letter designators for the scores, let's add some defines to make the display code easier. I'll adjust those first. That should help. Well, we'll need to include those defines. We'll need that clock for the 555. I'll make a common selector for the mux funnel. They all use the same value. Now we can start with the A-bit handler. Each front-end multiplexer handles 1 bit weight, feeding the segment decoder. Now the B-bit handler. Then C. And finally the D handler. I'll get rid of that space. And player 2 should have the underscore. Well, I've got an extra N there. Add a 7-segment decoder. It'll be a lot easier to use those segment names before we wire up the selectors, so let's go add some defines for that. Add the horizontal segment selectors. Add the vertical segment selectors. Add that fake timer. There's a lot of traffic in this output section, so we can break this up a bit. I'll call this segs mix since we're already using segs for the decoder output bus. The PLNR label is on the original schematic, so I'll make that line. Top is also on the legacy schematic. Now we can make score enable. I'm going to call this point segs out. Remember, we're generally using lowercase for labels we make up, generally. And finally, we can assign the score output. The spare 7474 gate was just used as an inverter, so we don't explicitly need it. I'm missing a semicolon there. Same mistake with player 2. Copy that signature and drop into main. Create the single output wire and connect it up. We don't have those score counters yet, so I'll set player 1's score to 1, 2, 3 and player 2's to 4, 5, 6. We can now connect that score output to the video mixer. Turn that on. Well, everything's in the right place, but those digits are wacky. It kind of looks like the vertical segments are swapped between the left and right sides. Well, the selectors for that look okay. You know what? We've got our defines backwards. Segment A is the highest order bit. Fix that. Turn that back on. Looks good. Start a one-player game, and player 1's score starts flashing. I've always thought that the flash rate is really annoying. Epileptic. I gotta back that down a bit. Let's drop defines for those. We won't make them switch configurable, but at least you can easily change the rate in code. Turn that on. Much better. Miss the ball and it shows the next ball number. Reset that and start a two-player game. Miss the ball and player 2's score flashes. A real quick test to make sure 7, 8, and 9 work. Yep. And might as well try out those hex digits. Nice. Alright, looks like the display is working. Now, we haven't run into any issues yet, but I keep wondering if this whole thing will fit into that FPGA. When we were at this point in the breadboard build, we had about 70% of the chips installed. We can check utilization by issuing APIO's report command. At the bottom, you can see that they profile a bunch of lines and their max reliable speeds. You can see here that we're using the low frequency oscillator, and here they show that the global buffers are 100% utilized. This is almost always the case because the compiler will assign the most highly used signals to global buffers. It also shows that we're using only 23% of GPIO. On the Arduino, we only have access to 40 pins, and some of those are reserved, so we are currently using about 60% of the I/O. The important number we're after here is LC, showing we're only using 11% of the logic cells. Looks like we have plenty of room to spare. Makes me feel a lot better. We can also check if we have any flotsam by issuing APIO's lint command. I'm surprised it's not dirtier. Looks like we have volley defined in 2 places in the ball motion logic. I remember we added the volley counter as an output to the port list so we could show it on the hex display. I'll leave it in the output so we can use it later, and we'll remove the internal one. Our dirty laundry is now lint-free. Okay, now that we have the display, we need the scores. So we'll see you in the next video.